Hmm?
Is today the start of?
It's one of the acronyms. Yeah. After the midterm, so basically the week before, well, actually we have a couple
It's
weeks.
a couple weeks, yeah.
We're going to learn a method called the simple method,
Okay.
which is
it
not
really?
simple.
I was gonna say.
It's not
sick.
actually simple.
Okay.
It's an acronym for another thing.
Great.
What's funny is that, and this will make more sense when we get there, but there's an alternative method for simple, which we're not going to learn in this class, called PISO. Um, and then someone thought to combine the two. So they thought to combine PISO and simple. But then the unfortunate acronym for that is PIM.
Yeah.
CFP people love their acronyms.
Then tomorrow your office hours at 2:30, correct?
No, actually tomorrow office hours are 1 to 2.
Write
Yeah.
that down.
Mhm. That's because I do walk-in advising from 2 to 3 on Thursdays.
Yeah. Room is corner room on the second floor.
Yeah, E220. Yeah, so go up the stairs and then turn right.
To the one below
Dr. Lee's.
Dr. Lee. You're
Yeah.
correct. That's the word. I was trying to remember that.
Yeah. Yeah, I'm right below his office. All right, it's 4 o'clock. Let's go and get started. Good afternoon, everyone. How's everyone doing today?
Good.
Good to hear. Okay, so it's the last lecture before the midterm. So normally I don't like to cut it this close, but it's just kind of taken a bit longer than I thought to cover convection. So we're going to finish that up today. We're going to do one example today. I think will hopefully help you with the last problem in the homework. I know that one's kind of a doozy. So we'll do that one together today. Um, and then the last thing I want to talk about today is the quick scheme. Now, a quick scheme is not going to be on the midterm. It wasn't on the homework, so it's not something I expect you to know, but it is something just good to know about CFD in general. So this part of the class, I'm kind of moving up a little bit. Normally I had it planned for later on, but since we're talking about convection and upwinding and finite volumes, I thought I'd move it up to this part of the class. So if you're kind of following along with the order of the lecture notes, we're basically jumping from lecture notes 8 to lecture notes 12. But we're only covering just a small portion of this. So again, so quick scheme, not going to be on the midterm, but just good to know in general. Okay, so I'll make an indication today. So once we're kind of done with the midterm stuff, I'll go ahead and kind of draw a line so that and then everything after that line you are not responsible for the midterm. Okay. All right. Any questions I can answer before we get started for today? Okay. Sorry, my video is not working, but I just wanted to check to make sure the mic was working. That's why I had a weird inflection on that one. Okay, all right, so let's go ahead and get started. All right, so where we left off, actually, let me kind of scroll up so you can see. Okay, so where we left off was that we were looking at 2D convection diffusion problems with finite volumes. Okay, so we're done with all the 1D stuff. So we're basically taking our 2D convection diffusion equation and then discretizing it using finite volumes. Okay. And so what resulted from this, just like we saw with 2D diffusion, when we applied our finite volume method to our 2D cell, was that we essentially ended up with 4 face integrals, right? We ended up with a face integral on the north, south, east, and west edges of the upper finite volume cell. Okay. All right, and so last time we kind of worked through the discretization, we kind of saw how it all worked, right? We went over the central scheme, the upwinding scheme, and we ended up with some equations over here. Okay. Now the one thing we didn't do, and the one thing we have to do before we do an example, is we have to go over how to apply boundary conditions. Okay, so let's go and start with that. Okay. Okay. All right. So once again, let's go ahead and let's go ahead and start with our Dirichlet boundary conditions. So remember, Dirichlet boundary conditions, these are boundary conditions where we are specifying the solution value directly. Okay. All right, and then just like before, we're going to do an example just to kind of show you the method that you can use to apply these boundary conditions, just because, remember the exact form and the exact formula that we end up getting depends on where the boundary condition is, right? So whether it's on the north side, the south side, the east side, the west side. So, it's good to kind of know this method and to apply it accordingly. Okay. Okay, so let's look at a situation where we have a Dirichlet boundary condition on north edge. Okay. Okay, so we have a situation like this. So we have our cell of interest. Okay. So this here is phi sub c, right? So that's a cell where we're going to be deriving these finite volume equations for. We have a neighboring cell on the east side, phi sub e. We have a neighboring cell on the west side. This is phi sub w. And we have a neighboring cell on the south. So that's phi sub s. Okay. And then on the north edge, we have our Dirichlet boundary condition where we say that the our value for phi is going to be known all along that edge. Okay. Okay. And so just like we usually do, let's derive or let's determine the finite volume equations for this center cell. Okay. All right. So first thing we notice here is that we do have neighbors on the east, west, and south edges. Okay. Okay. Right. And so for those edges, we can evaluate our line integral on those faces as normal. Okay. Except with convection, we do have one additional complication. We need to ask ourselves whether or not we're going to do upwinding in those directions. Okay. Okay. Because if upwinding is required, that's going to change how we discretize the convection term in those lines. Okay. So that's kind of the main difference. And you'll see that in the kind of the fully worked out example that we'll do after this. When you're doing convection, is that you always kind of need to ask that question of whether or not upwinding is needed. And that affects how you evaluate your integrals. Okay. Okay. So remember the way that we determine upwinding is we compute the Peckley number, right? And there's two Peckley numbers that we need to determine, right? So we have the Peckley number in the x direction, the Peckley number in the y direction. So in the x direction, we have u multiplied by delta x divided by k. And then in the y direction, we have v multiplied by delta y divided by k. Okay. Right. Now, you could have a situation where you need upwinding in one direction, but not in the other direction. So just be aware of that. Okay. And for finite volumes, it's actually okay. So, if you end up doing upwinding in one direction, you can still use the central scheme in the other direction. For our purposes, that's okay. Okay. Now, of course, in order to compute these, we need values for the velocity and the diffusion constant and the grid spacing. But for this kind of simple example here, I'm not going to bother putting numbers in here. But let's just say for the sake of argument that the Peckley number in the y direction is going to be greater than 2. Now, for a real problem, you don't have to assume this. You just plug in the numbers from the problem. But just for this simple example, let's assume that we need upwinding in that direction. Okay. Whereas for the x direction, we're actually okay. So, let's say we plug in our velocity, our x velocity might be really small. And we don't have to do upwinding there. So for the x direction, we can just use our simple central scheme. Okay. Okay. And then now that begs the question, if we are doing upwinding, which way is the velocity going, right? And so for this particular problem, let's say that the velocity is going that direction. Okay? So our v velocity is positive. Okay, so let's prepare all four of our integrals here in that sense, okay, as well as the boundary condition. Okay, so east and west integrals, those are basically staying the same, right? So our east integral here is going to be integral. Actually, let me just start. Well, let's write the whole thing first, right? So we have integral of phi multiplied by u minus k partial phi partial x. Okay. ds. Right. Right. And so we evaluate this using trapezoidal rule. We get e sub little e times u minus k partial phi partial x on the east face. Okay. Right. All right, now comes time for the discretization. So, we know that in the x direction, we don't need upwinding, right? So for phi sub little e here, we're just going to use our central scheme, right? So this is going to be phi sub big E plus phi sub c divided by 2, okay? And then for our diffusion derivative here, diffusion's always the same. We don't need to, do anything special for upwinding here. So this is going to be phi sub E minus phi sub c divided by delta x. By the way, I realize I've been doing this for weeks now, but I don't think I ever explained the convention here. So, when I plug in this finite difference approximation for the diffusion derivative, right? Some of you may have noticed that sometimes I put phi sub c first, and sometimes I put phi sub c second, right? Right. So the question is, when do you put phi sub c first or phi sub c second? Okay. So if you're kind of good at memorizing rules. So for the east and north integrals, right? Those are situations where you have phi sub c going second. Because if you think about it, the east and north sides, those are the directions of positive x and positive y. So east is positive x and north is positive y. Okay. Whereas for the south, or I guess for the west and south integrals, phi sub c goes first. And the reason for this is that the west direction, this is the direction of negative x, and the south direction is the direction of minus y. Okay. Okay. So I've been doing this for weeks, and I don't think I ever explained it, but that's kind of the reason why why you have the certain orders for phi sub c and its neighbors. Okay. All right. So with this equation here, there's nothing nothing too complicated. We have no boundary condition. We have no upwinding. So we just kind of plug in and evaluate, right? And so this is u times phi sub e plus phi sub c divided by 2 minus k phi sub e minus phi sub c divided by delta x. Okay. Okay. The unfortunate thing with convection is because there's so many different, I would say kind of decision branching paths, whether you're doing upwinding, no upwinding, boundary condition, no boundary condition. Sometimes there's just kind of no choice. You kind of just have to go straight from the integrals and just evaluate everything. So these problems do take a while. So the last problem probably will take you a bit of time. But it's kind of good practice to kind of think about kind of what are all the decisions you have to make. All right, any questions on this? Okay. All right, so let's do the same thing for the west. And so for the west, we also don't do anything special. Okay. So for the west integral, we have, and I'm going to skip the integral part. I'm just going to skip straight to the evaluation. So we have a minus phi sub little w times u plus k partial phi partial x in the west direction on the west face. Okay. Once again, we don't have any upwinding in the x direction, so we just plug in our central scheme. So this is phi sub big W plus phi sub c divided by 2 times u plus k Since we're on the west face, we're going to do the opposites. We're going to have phi sub c going first, minus phi sub w, all divided by delta x. Okay, good. Okay, so now let's do the south integral. So for the south integral, after we apply our divergence theorem, after we kind of apply our integral, we end up with the following expressions. We have minus phi sub little s times v plus k partial phi partial y evaluated at the south face. Okay. Okay. Now for this one, remember, we do need upwinding here, right? That was kind of what we determined earlier in the problem. And so when we plug in for the face value of phi sub little s, we're going to plug in its upwinding value, not the central scheme, okay? So for upwinding, for this particular problem, we're upwinding from the bottom going up, right? So that means for our upwinding scheme, we're going to plug in phi sub s. Okay? And I know it's hard to determine, the difference between lowercase s and uppercase s, but this is phi sub uppercase s. Okay? So that phi sub big S there, that's the self-centered value on that south side. Okay, so we go and plug that in. We get minus phi sub big S times V. No averaging there, no central scheme because, we are upwinding. Plus K multiplied by phi sub C minus phi sub big S divided by delta Y. Okay. That's our south integral right there. Okay. All right. All right, and then finally we get to the edge with the boundary condition. Okay, so now we go to our north edge up here. Okay, so our north edge has that boundary condition. So remember, when we have a Dirichlet boundary condition, that kind of affects our convection and diffusion terms a little bit different. Okay, so our north integral, we have a positive phi sub little n multiplied by v minus k partial phi partial y evaluated on the north face. Okay. I just realized something I forgot here. We'll circle back in a second. I forgot the edge length for each of them, but we'll come back to that. All right, so for the north integral, we have phi sub little n, right? So since we have the boundary condition on this edge, that means the value for phi on that north edge, we're just going to plug in the Dirichlet value. So, we have no neighbor on the north side. We just have the boundary condition. So for phi sub little n, we're just going to plug in phi naught. That's our boundary condition value. Okay. And then our diffusion derivative, right? We're going to make a finite difference approximation here, but we're only going to go a half. Okay, so just that half length finite difference is something that we've seen for a few weeks now. Okay. Okay, so we go ahead and do that. We get B naught times V minus K phi sub naught minus phi sub C divided by delta Y divided by 2. Where, of course, everything with phi naught here, these are known quantities, right? Because we know what the boundary condition is. So everything with phi naught, we move it to the other side of the equation. All right, and so the solution for this, and so I'm not going to do it just for the interest of time, right? We have the values of all four of our integrals now. Okay, the only thing left to do is to take those four results and just add them together. Okay, and that essentially is the evaluation of our integrals for that cell. Okay, so the one thing I forgot before I open it up for questions is that remember when we're evaluating these integrals, we're doing so with the trapezoidal rule. So one thing we need to do is we actually need to multiply this by the edge length. Okay, so we're gonna have a delta y multiplied by the east integral. Okay, we're also gonna have a delta y multiplied by the west integral. We're gonna have a delta x multiplied by the south integral, and we're going to have delta x multiplied by the north integral. Okay, so these grid spacing that we're including here, these are a result of our trapezoidal rule. Okay. I apologize. I know that example was kind of a little bit all over the place, but we'll do a couple more. Hopefully, I think we'll make it a bit more quick. Okay. Okay. Any questions on this example here? Yes.
Going back to the cell one.
Yep.
Can you explain again the little s versus big S in the whole cell center value?
Yeah, sure. So remember, when we evaluate these integrals, we're evaluating them on the edge of the cell, right? Right. So for that south integral, we're essentially integrating along that edge right there. So phi sub little s actually kind of straddles the line right in between these two cells, right? So phi sub, this is little s. Right, so phi sub little s is the value of phi on the edge in between the two cells, whereas phi sub big S is the cell-centered value for our neighboring cell, right? So that's not our center cell, that's the cell next to us. Yeah, so I use lowercase letters to denote values for phi on the edges of the cell, and then uppercase letters for the cell-centered values.
So the upwinding is against it, so it would be the biggest.
Exactly.
Okay.
Yeah.
Thank you.
Mm-hmm. All right, any other questions? Yes.
Yes, so if we have a bigger grid, like will that instability in the y direction will it affect other grid points in the y direction?
Yes, and so if you didn't use upwinding here, so you had a Peclet number greater than 2, then that instability will kind of propagate kind of everywhere. It'll start here, but then the thing with instability is that it just kind of ends up just polluting everything essentially.
So are we, in that case, are we using central differencing of the x direction only, and then y just opening?
Exactly. Exactly. Yeah. Yeah. So we use upwinding everywhere in y, but for x direction, since we're stable, we can use central differencing for that.
Okay.
Yeah. Mm-hmm. All right. Any other questions on this? Okay. All right. So let's do another example. So let's do one with the Neumann boundary condition. All right, so we'll do one more example with just kind of symbols, and then we'll kind of put it all together with the example with some numbers. Okay. Okay. So let's say for this example, let's say we have a Neumann boundary condition on the east face. Okay. Okay. So once again, I'm going to draw our cell in question. So this is going to be phi sub c. We're going to have a neighbor to the north. We're going to have a neighbor to the south. We're going to have a neighbor to the west. Okay. And we're going to say that our Neumann boundary condition on the east is given by some value gamma. Okay. Okay, and so once again, let's write out the finite volume equations for phi sub c. All right. So we're going to operate under the same conditions as the last problem. So let's assume that we are doing upwinding in the y direction. Okay. Whereas for the x direction, we're just going to use our normal central scheme. And then just like the last problem, we're going to assume our velocity is going from the bottom up. So that means our upwinding is that we're going to take everything that's on the south side. Okay. All right. So let's actually start with the boundary condition this time, just because just so that we use the same order. So let's go east integral first. Okay. Okay. So remember, for Neumann boundary conditions, when we have a convection term, right? So this is kind of what we discussed on Monday. We kind of simplify our entire process here, and we just say that we're just going to replace the entire integral with that Neumann boundary condition. Okay. All right. So our east integral here, we have b sub little e multiplied by u minus k partial b partial x on the east edge, okay, multiplied by delta y. Okay. Didn't forget the edge length here. Okay. All right. So for the Neumann boundary condition, we're just going to say that everything in the parentheses here, right? Everything in the parentheses here is going to be replaced with the Neumann BC. So for Neumann boundary conditions with convection and diffusion, we just kind of make it simple, right? So like I said last time, there is a way to deal with it that's not so simple, but we just kind of get bogged down in the details, and there's already kind of a lot of details to see here. Okay. Okay, so our east integral here is very simple, right? And so we end up with a value of just gamma multiplied by delta y. All right, so very straightforward. And once again, gamma here, its value is known because it's a boundary condition. And so we're going to move that eventually to the right-hand side of the equation alongside the source term. Okay. Okay, so let's go through all the other integrals here, and we'll go kind of fairly quickly. Okay, so let's do the north integral now. So north integral is going to be phi sub little n multiplied by v minus k partial phi partial y, evaluate on the north face, multiplied by that edge length, which is delta x. Okay, so we're going to do upwinding here. So that means we're going to replace phi sub little n there with its corresponding upwinding value. So let's go back to the figure here. And remember that phi sub little n, right? Phi sub little n is the value for phi that's in between our central cell and our north neighbor. Okay, so if we're going to do upwinding here, and we have a choice between phi sub c and phi sub n, we're going to pick the value of phi that's on the upstream direction, which in this case is phi sub c. Okay. So remember, when you do upwinding, you have to pay attention to which direction the velocity is going, and you're going to pick the value for phi that's upwinding on there. Okay, so wherever the velocity is coming from. Our diffusion derivative stays the same. And so when we evaluate this, we get phi sub c multiplied by v minus k phi sub n minus phi sub c divided by delta y, all multiplied by delta x. Okay. All right, and then now let's do the West integral. So West integral we have minus phi sub little w times u plus k partial phi partial x evaluated on the west face, all multiplied by delta y. Okay, our trapezoidal rule length there. Okay. Okay, so in the x direction, we don't need any upwinding, so we can just use our central scheme for that. And so we have a minus phi sub little w here. That's going to be the average of phi sub big W plus phi sub c divided by 2 multiplied by u plus k phi sub c minus phi sub w divided by delta x, all multiplied by delta y. And then on the south integral, we'll just do this one very quickly. We have a minus phi sub little s multiplied by v plus k partial phi partial y evaluated on the south face multiplied by delta x. Okay. All right, so once again, for the south integral, this is an integral in our y direction, so we are going to do upwinding here. Right, so phi sub little s, we're going to apply upwinding. And then we once again look at our figure here to see which direction is the upwinding one. So remember, keeping in mind that this is phi sub little s that we're evaluating in our integral, right? So phi sub little s here is between phi sub c and phi sub big S. And so the value for phi, the self-centered value that's on the upwinding side, is phi sub big S, just like the previous example. Okay, so we go ahead and plug that in. We get minus phi sub big S multiplied by v plus k phi sub c minus phi sub s divided by delta y, all multiplied by delta x. Okay. Okay, and so there we have our 4 integrals that we've evaluated for this problem. Kind of zooming out so you can kind of see all. Okay. All right, so lots of decisions to make, and I know I kind of went quickly here, but hopefully when you're kind of looking at this back again in your notes, you kind of understand kind of every kind of decision, every kind of micro decision that you have to kind of make along the way, whether you're going to do upwinding, no upwinding, central scheme, upwinding scheme, what to do for the diffusion derivative, whether you're going to do a boundary condition. Okay. Okay, any questions on this? Okay. All right. So let's do a real example here. So let's do one with numbers. So this is actually quite similar to your homework problem. Okay. And you'll kind of see all this kind of in action again. And so, with these kinds of problems where, I would say, the devil, these are the kinds of problems where the devil is in the details. You kind of just have to get a lot of reps. You have to kind of get in a lot of practice just so that you kind of, your mind kind of gets into that practice of, making these decisions. But I think, when you're doing these long problems, it's very easy to kind of gloss over certain things and try to just kind of plug into a formula. But, the more practice you do, it becomes easier to see. Okay. All right, so let's do an example here. This will be the last example for the day. Okay, so let's consider the following equation. So we have 50 partial phi partial x plus 5 partial phi partial y, okay, minus 2 partial squared phi partial x squared plus partial squared phi partial y squared is equal to 3xy. Okay. Okay. All right, and then let's say that we're solving this equation on the following grid. Okay. So we have basically a grid that's 4 cells in each direction. So this is cell 1. Sorry, computer. Okay, I think I'm back. Okay. Can you guys hear me on Zoom?
Yeah, we can hear you.
Yes.
I hope. Okay, good. Okay, good. Sorry, my computer kind of conked out for a second. Okay. Right, we're numbering this out. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. All right, and so we need boundary conditions here. So let's say that on the south edge here, we have partial phi, partial n is equal to 0. So we have a Neumann boundary condition of 0. Left-hand side, we have a Dirichlet boundary condition. We say that phi is equal to 50. Right, on the right-hand side, we have phi is equal to 25. And up top, we have phi is equal to 50. Okay. Okay. We also need our grid spacing. So let's say that delta x is equal to delta y is equal to 0.25. Okay. All right. So for this problem here, we're going to solve for the finite volume equations for certain cells. We're not going to do all of them. That's crazy. That would take us the rest of the lecture. So let's just choose a couple of them. So let's do cell number 6. Okay. And let's do cell number 4. So determine FV equations for cells 6 and 4. Okay, so we have one interior cell and one corner cell, right? So I think that's only appropriate just because, for the 2 previous examples we did cells with just a single boundary condition. So, the only thing that's left are just interior cells and a corner cell. Okay. Okay. All right, so that's the setup for the problem. So first thing we're going to do is we are going to compute the Peclet numbers and see if we need any upwinding. So make sure you do that before you start writing finite volume equations. Okay. So we're going to compute the Peclet number in the x direction, Peclet number in the y direction. Okay. Okay, so Peclet number in the x direction, we have u multiplied by delta x divided by k. And Peclet number in the y direction is v multiplied by delta y divided by k. Okay. All right, and so in this problem, we actually have some numbers here. So, we can actually, see whether it's stable or not. Okay. Okay. All right, so let's do in the x direction first, right? So from our problem here, we see that our u velocity is 50, okay? Our k value is 2, right? And our grid spacing is 0.25, okay? So you can probably already see that we're going to be unstable. Okay, so we go ahead and plug in. We plug in 50 multiplied by 0.25, okay, divided by our k here, which is 2. Okay. All right. So we plug all those numbers in, we essentially get 50 divided by 8. Right, so which is 25 over 4, right? Right, so that of course is 6.25, which is greater than 2. So that means we're going to need upwinding. In the x direction. Okay, now let's do the same thing for y here. So we're going to plug in our same variables here, except for the y direction, we're going to plug in v, which in this case is 5. Okay, so we have 5 multiplied by 0.25 divided by k, which is 2. Okay. So you can already tell, right? Because just the magnitude of v is 10 times less than the value of u, right? And so this is going to end up with 25 over 40, which is divided by 5 over 8. And so this is less than 2. Okay. So for the y direction, we do not need any upwind. So for any y derivative, any y integrals, we're just going to use our central scheme for that. Okay. All right, good. Okay, so let's go ahead and evaluate these integrals. So let's start with cell 6 because that's our interior cell. Okay. All right, so we're going to evaluate our 4 integrals here, and but applying upwinding when we. Okay. Okay, so let me go ahead and let's write out basically 4 lines here for our integrals. We have the east integral, the north integral, the west integral, and the south. Okay. By the way, you can do them in any order. I just choose to do east, north, west, south, just so I do the positive x, positive y, negative x, negative y. But you can do whatever order makes sense to you. Okay. Okay, so just like our previous example, let's go ahead and plug in. So then our east integral here is going to be positive phi sub little e times u minus k, partial u, partial phi, partial x, evaluated on the east face, multiplied by delta y. Okay. Okay, so here, we can actually plug in the numbers for this. So we can plug in for u and k, right? But the more important thing here is that we have to do upwinding. Okay. Okay. So we're doing upwinding in the x direction. Okay. But remember, we need to determine which way we're going to upwind it. Either going to upwind from the left or from the right. Okay, so for this case, our u velocity is positive, and so we're going from left to right. That means when we upwind, we're going to upwind from the west direction. Okay, that means for phi sub little e here, right? Since we're on the east face, the cell that's immediately on the west of that is going to be phi sub c. Okay, so this is phi sub c multiplied by u, which is 50, okay, minus k, which is 2, multiplied by the derivative, so that's phi sub e minus phi sub c, all divided by delta x. Okay, and we're going to multiply that by delta y. Okay. And one more parenthesis. There we go. Okay, I knew something was weird. Okay, so now on the north integral, we're going to have the exact same thing, except we're going to replace everything with the north, right? So this is going to be phi sub little n multiplied by v minus k, partial phi, partial y, evaluate on the north face, multiplied by delta x. Okay. All right, so no upwinding is needed for the north side, so we're just going to plug in our central scheme for the north integral here. Okay. Okay, so we have 5 multiplied by phi sub big N plus phi sub c divided by 2 minus 2 phi sub n minus phi sub c divided by delta x, or delta y, excuse me. and the whole thing multiplied by delta x. Okay, now let's do the west integral. So remember, for the west and south integral, since those are on the negative side, we kind of flip the sign of every term in our integral here. So we have a minus b sub little w multiplied by u plus k partial phi partial x evaluated on the west face multiplied by delta y. Okay. All right, so we do have upwinding here, so we need to make sure we apply that. So for phi sub little w, the upwinding phi value that's on the west side here is just going to be phi sub big W, right? We plug in for that, we get minus 50 phi sub big W, okay, minus 2, or plus 2, excuse me, phi sub c minus phi sub big W, all divided by delta x, multiplied by delta y. Okay. All right, and then finally we have the south integral. So this is minus phi sub little s multiplied by v plus k partial phi partial y evaluated on the south face delta x, okay, is equal to, we have a positive 5 multiplied by phi sub big S plus phi sub c divided by 2 plus 2 minus 5, excuse me, plus 2 times phi sub c minus phi sub s divided by delta y, everything multiplied by delta x. Okay. Okay. So hopefully, hopefully this kind of process of evaluating these integrals, this is, I think, the third time we've done this today. So hopefully it's getting to be a bit more regular. Okay. So one thing we'll do here that we didn't do in the previous examples is we are going to actually add all these things together. Okay. Okay, so we add all these things together. That's essentially going to be our left-hand side of the equation, right? All right, so we have let's see. So I'm going to do all the convection terms first, and then I'm going to do all the diffusion terms after that. Okay. All right, so we have a 50 b sub c plus 5/2 phi sub n plus 5/2 phi sub c minus 50 phi sub big W, okay, minus 5/2 phi sub s minus 5/2 phi sub c. Okay. Right, so everything in that parentheses there, that's just all the convection terms here. So I basically took everything here, okay, and I just added those together, and we ended up with that expression right there. Right? I haven't simplified anything. I just basically took everything, I distributed, and I just kind of brought them down. Okay. Okay. The reason I did that is because the diffusion terms are actually much simpler. Okay, so the diffusion terms, they kind of always have the same pattern, especially for an interior cell, right? So for the diffusion terms, we have 2 divided by delta. Okay, I'm going to make use of the fact that delta x and delta y are the same. Okay, and so I'm just going to plug in a generic delta there. Right, so you have plus 2 over delta multiplied by, right? We know what this one is just because we've seen this kind of so many times now. Okay. Okay, so we have a positive 4 phi sub c minus phi sub e minus phi sub n minus phi sub s minus phi sub big W. Okay. Right, and so that whole thing is multiplied by delta. Remember, that delta there comes from the trapezoidal rule. Okay, so this delta is the same as basically these guys out here. Okay. So don't forget that. It's a very kind of easy, it's a very easy detail to miss for these problems. Okay. Okay. And then one thing that we haven't seen in the example today, but we've seen this before, is we have our source term, right? So through all this madness, we forgot that we have a source term on the right, which is this 3xy. Okay. So we integrated that as well. And so on the right-hand side, we have 3xc yc multiplied by delta squared. Okay. All right, and so last thing here is just to simplify. Okay. Okay, and so simplifying this is not an easy task, but you can kind of do it in theory, right? Because eventually, when you kind of plug everything in, you distribute everything, you're going to get kind of singular coefficients for each of the phi values, right? So it's a coefficient for phi sub c, coefficient for phi sub n, coefficient for phi sub w, phi sub s, right? So on and so forth. Okay. Yeah.
Sorry to interrupt.
Mhm.
On the exam, if we don't have time to simplify, but we have those like expanded expressions, is that acceptable?
Yeah, perfectly fine. If you end up with this on the exam, that's 9 out of 10. So yeah, definitely you want to be strategic with your time on the exam. So simplify when you can, but make sure you at least get it to a point where I know that you are doing the process. Right. I told this to my 308 kids yesterday too, where when I grade exams, I'm mostly grading you guys on process, right? Especially for a class like this where it's so heavily dependent on the process, right? These processes are complicated, right? You can see it's taking us a long time just to do this process here. There's a lot of details. And so if you can kind of show me that you know the process and you can implement it correctly, details of the math aside, and that to me is the vast majority of the points for sure. Yeah. Mm-hmm. Right. And in fact, we don't have time to simplify today. So, kind of a good illustration for that. We may not get to quick scheme today, but that's okay. I want to make sure I get these examples done because this is relevant for your exam. This is relevant for your homework. We can always do quick scheme after. All right. Any questions on this this part of the example here? Okay. All right. So then let's do the same thing, but then we're going to do it for the last cell here, which is cell number 4. Okay. Now cell 4, as you can see, is a corner cell. And so that means we're going to be applying boundary conditions on this cell. Okay. So we're going to apply boundary conditions on the south side and the east side. Okay. Okay. So once again, let's write out our 4 integrals here. So we have the integral on the east, on the north, on the west, and the south. Okay. And we're going to go through the exact same exercise as before. Okay. Except, right? So there's a reason, when I did this derivation for cell 6, right? I did everything in terms of generic, neighboring cell, terminology here, right? So phi sub c, phi sub w, phi sub e, right? Technically, when we're applying this to cell 6, right? We could have easily plugged in, the values for each of these, symbols, right? So instead of phi sub c, right? Phi sub c is technically phi 6 for this cell, right? Phi east. The east neighbor for cell 6 is cell 7, right? The north neighbor for cell 6 is cell 10, right? But I didn't do that, right? So I did everything in terms of generic, neighboring, terminology here. And there's a reason for that, because I knew, right? because I wrote the problem, I knew that, we're eventually going to be doing this for multiple cells, okay? Because if you look at this problem, right, the velocities and the diffusion coefficients, they don't change, right? So they're basically constant, so they're not functions of x, right? And so what that means is that for cell 4, where we have neighbors on the west side and the north side, that means those expressions are going to be the same as what we determined before. Okay. Okay. So when you guys are doing the homework, right? So make sure you make some observations like this, especially for the exam too, because you don't want to be doing this too many times. Otherwise, it's going to take you a lot of time, right? So if you notice a situation like this where you can reuse an integral, right? You write your solution here in terms of the cell, generic neighbors. You can just use those exact same expressions down here. Okay. Okay, so let's go ahead and do that. Right. And so for the north integral here, I'm just going to go ahead and drop this down here. Right. So for the north integral, we have 5 b sub n plus b sub c divided by 2 minus k, which is 2. Sorry. Okay. 2 phi sub n minus phi sub c divided by delta y. Okay. Entire thing multiplied by delta x. Okay. Let me just double check that that's true. Yep. Okay. And then for the west integral, we have minus 50 multiplied by phi sub big W plus 2 phi sub c minus phi sub big W divided by delta x, everything multiplied by delta y. Okay, so exact same expressions we had on the previous one. Okay. So my strategy, usually when I tackle these kinds of problems and I'm asked to, find the finite volume equations for several cells, I start with an interior cell. Just because the interior cell has a neighbor on every side, just because most other cell, or basically every other cell in the grid here is always going to have at least 2 neighbors, right? So if you do the interior cell first, right, you kind of get the hard work out of the way, then you can reuse a lot of the results from the interior cell for the other cells in the grid. Okay. All right, so this is tip. Do interior cell first. Right, you do that, and that kind of saves yourself a lot of work for these kinds of problems. Okay. Okay. All right. So our north integral and west integral are kind of squared away. They have the exact same expressions as before. Right. So let's look at the east and south sides. Okay. Okay. And so on the east, for the east integral here, we have a Dirichlet boundary condition of 25. Okay. Okay. So let's factor that into our equation here using the same method that we went over earlier in class today. Okay. Okay. So for the east integral, we have positive phi sub little e multiplied by u minus k, partial phi, partial u, or partial phi, partial x, evaluated on the east edge, okay, multiplied by delta y. All right, and so we're going to modify this expression to account for that Dirichlet boundary condition. So phi sub little e here, that is our Dirichlet value, which I forgot what it was already, 25. Okay, so our Dirichlet value here is 25. Okay. Multiplied by our velocity here, which is 50, okay, minus 2 times our diffusion derivative, which remember, we're going to do it on the half length. Okay. So the half length derivative for this is phi sub big E minus 25, or excuse me, phi sub, yeah. So we're going to use the Dirichlet boundary condition on the right side. So this will be 25 minus phi sub C divided by delta X divided by 2. And that whole thing multiplied by delta y. For again, this 25 here, that was our Dirichlet value. Okay. Good. Any questions on this so far? Okay. All right. So last integral here, I saved the best one for last, right? On the south integral here, we have a Neumann boundary condition of 0. Okay. Okay, so let's write our expression for the Neumann for the south integral, excuse me. So this is minus b sub little s multiplied by v plus k partial phi partial y, evaluate on the south edge, multiplied by delta x. Okay. So we are in luck. So a Neumann boundary condition of 0 is the best situation because that means we can just take this entire thing in here and plug in 0. Okay. So that means our south integral here, very simple. We just end up with a 0. All right, and so we have the same situation as before. So let's we can go ahead and simplify this, and let's actually do this because I've kind of decided at this point we'll save the quick scheme for another time. So let's go ahead and simplify this fully, and then you can kind of see kind of what their end result looks like. Okay, so once again, we're going to take these 4 integrals, we're going to add them all up together, and then we are going to set that equal to the source term on the right. Okay, so first let's do all of our convection terms here. So convection terms, we have a 25 times 50, that is 1,250. Okay, then we have 5/2 times phi north plus phi c. Right, so that came from the north integral. From the west integral, we have a minus 50 bw. Okay, and then from the south integral, we have just a 0. Okay, so this right here is all of our convection terms. So luckily, there's no overlapping terms here, so there's nothing to simplify yet. Okay. All right, and then for our diffusion terms, they are all the same. Okay. Okay, so we have a plus 2 divided by delta multiplied by 4 phi sub c, or not 4, excuse me. We only have 3, right? Because we have our south integral here. Actually, no, we do have 4. I apologize. Let's do all of them together. I'm sorry, things were complicated because of the boundary conditions. Okay, so for our diffusion terms, let's start with the contribution from the from the east integral here. Okay, so this is 25 times 2, which is 50. Okay. Right. A minus 22 times 50 is plus. No, it's minus. But so you can see how things get hairy here with the signs and all this stuff, right? So first term here we have a minus 25/2, right? Because we have a minus sign here, and this is 25 multiplied by 2, which comes from the denominator. Okay, I've already factored out that delta x, and I've kind of brought it out in front here. Okay. Okay, so we have a minus 25 times 2 plus 2 times phi sub c. Okay. All right, then we have a minus phi sub n plus phi sub c. Then from the west integral, we have a plus phi sub c minus phi sub w. Okay. All right, and so that gives us all of our diffusion terms. All right, and so let's go ahead and combine the like terms now. Okay, so we combine like terms here. We basically we know delta, right? So since delta is equal to 0.25, right? That means 2 over delta here is basically 2 times 4, which is 8. Okay, so we go ahead and simplify this. We get 1250 that comes down plus 5 over 2 b sub n plus 5 over 2 b sub c minus 50 b sub w. Okay. We have an 8 times a minus 50, so that is a minus of 400. Okay. Plus 8 times 2 times phi sub c, so that's 16 phi sub c minus 8 phi sub n plus 8 phi sub c plus another 8 phi sub c minus 8 phi sub w. Okay. I'm sorry. I made one minor mistake here. It's going to be really annoying. So this phi sub s here should actually be a phi sub c. I apologize. So that's phi sub c right there. I'm kind of doing this one live because I don't have this one actually in my notes. So, you know, what you're seeing here is actually me working this out in real time. So you know, there's always bound to be mistakes when that happens, but so I'm just double checking everything, making sure everything's okay. Okay. All right. So let's go ahead and combine the like terms. Okay. So we combine the like terms we get. Let's do our constants first. And so we have a 1250 and a minus 400. So that is a positive 850. Okay. Let's do phi sub n now. So we have for phi sub n, we have a minus 8 and a plus 5 over 2. So minus 8 plus 5 over 2, that is minus 5.5. Okay. Okay, let's do phi sub w next. So phi sub w, we have a minus 50 and a minus 8. So that is a minus 58. Phi sub w. Okay. And then for phi sub c here, let's see. We have 16 plus 16, 32 plus 5 over 2. So that's 34.5. Okay, good. Good. And no unwanted neighbors, right? There should be no phi sub s, because remember, this is for cell number 4. It doesn't have a cell. Okay. Okay. And then we can't forget, right? All this is equal to our source term, which is 3 times xc and yc.
Grab the delta.
I did forget the delta. Thank you. I knew something was missing. So there is a delta right here as well. Okay. All right. So let's actually divide by the delta. I think that'll be a little bit more convenient than multiplying it through. Okay. So we divide both sides by the delta.
Let's have a delta squared on the
There's a delta squared there. Thank you. Okay, so we'll divide by delta. And that's going to eliminate one delta over there. I'm going to take the 850. I'm going to move it over to the other side because that is a known quantity. Okay. And so on the left-hand side, all we're left with is minus 5.5 b sub n minus 58 b sub w plus 34.5 b sub c is equal to 3 delta, which is basically 3 times 0.25. Okay. Okay. We need to plug in the coordinates for the centroid for this cell here. Okay. So let's go back to the figure here. We know the grid spacing in each direction is 0.25, right? And so the x coordinate for cell 4 here, right? So we're going to do 0.25, 0.25, 0.25, and then half of that. So the x coordinate is 0.875, and the y coordinate is 0.125, okay? Just 1/2 of a grid spacing. Okay. So that's 3 times 0.25 times 0.875 multiplied by 0.125. Okay, so that takes care of our source term, and then we're going to subtract 850. Okay. All right, and so I've been resisting this whole time, but I'm going to pull out the calculator for this one because I cannot do that in my head. Okay, so we have 3 times 0.25 times 0.875 times 0.125, which is basically nothing, and we minus 850. All right, and so we get our final answer here. And so on the right-hand side, we have a minus 849.92. And on the left-hand side, we have a minus 5.5 B sub n minus 58 B sub w plus 34.5 B sub c. All right. That's a doozy. All right. All right, so hopefully when you guys are doing this, you don't have dumb pride like me and you pull out your calculator earlier and you kind of compute these things so you're not kind of bringing all these symbols. Okay. Oh, one last thing, actually, I'm sorry. We can plug in actually the cell numbers here, right? So remember, phi sub c here, we all started this started as cell number 4, right? And so phi sub c here is phi 4, right? The west neighbor for phi sub c is cell 3. And the north neighbor for cell 4 is cell 7. Right. So we can drop the generic neighbor notation here. We can plug in the actual neighbors for this cell.
So 8, yes.
You're right. I cannot do math right now. Somehow, I think because I know the north neighbor is +4, so I think I did 3 + 4, which is 7. So, but you're right, it's 4 + 4, which is 8. Yep. All right. So note to self: don't do a live demonstration again. Just prepare these ahead of time. All right. Any final questions on this? Okay. All right. So thank you guys for coming today. Thank you for being patient with me through this example. We'll do quick steam another time, but this will be everything you need to know for the exam, and this will get you through the last problem of homework as well. So thank you guys for coming today. If you have any questions on the last problem of homework, remember I have office hours tomorrow, or you can send me an email. So next time I see you guys will be Monday for the exam. So best of luck studying, and I will see you guys next week.
Front and back.
Yes, front and back. Yes. Yeah. All good.
Thank you.
Yeah. I'll post the solutions for homework 3 tomorrow.
Gotcha.
Or Friday.
Yeah.
Okay.
What are the hundred conditions for this one?
Yeah. Flux is the same thing as Neumann.
Neumann.
Yeah.
You want me to?
Yep. This one right
It
here.
makes sense. I think it's how it's the problems. So how do we go from here? Sometimes they're.
Ah. Yeah. So the diffusion terms are basically everything. Let me just highlight them. So these are all our diffusion terms here. So I basically took. So I evaluated 2 over delta because I knew delta is 0.25, right? So 2 over delta is 8. So I basically distributed 8 throughout that entire parenthesis.
Okay.
Yeah, so we have minus 25 times 2 times 8, so that gives us a minus 400. And then we have an 8 times 2 times phi sub c, that's 16 phi sub c.
Okay, and then you can scroll down just a little.
Yep.
So. We bring everything together and then it simplifies. We bring like terms piece together and then it gets us this.
Yeah.
And then. How do we How do we still have delta over here?
Ah, so that delta is something I forgot. So that was something that should have been included up here. So there should have been a delta here, because if you look at all these integrals here, they all have this delta out in front. So that's one thing I just forgot to carry down as we were doing it.
Okay, but that delta, we don't transform it into 0.25.
No, because I just divided everything through, right? So basically, this, you can think of there's a delta kind of all throughout here. So there's a delta multiplying by all of this, right? There's that delta there. And so what I did was I just, I knew there's a delta here. I knew there's a delta squared over here. And so I said, a simpler thing, let's just divide by delta, just cancel that out. Just saves us from doing a little bit of arithmetic.
Okay, and then final question for maybe it was something along the beginning that I just left back in the XC and the XY. How did you get those values?
This XC and YC?
Yeah.
Yeah, so remember, this came from the source term. So this is basically the coordinates of cell 4. And so if you go back up to the figure here. Exactly. Yeah.
All right, sounds good. Thank you.
Yep.
One more question when it comes to the exam. So how's it going to be formatted? So there's going to be multiple choice questions for
Short answer questions.
short answer questions,
Yep.
4 of those, and then one free response, or
There's gonna be 3 free response questions. Yeah, they're not gonna be nearly this bad. This is way worse than what's on the exam.
okay.
Yeah, I took the entire exam, took me maybe like 25 minutes, and so, but I knew all the questions, and then the numbers were a lot more convenient. Mhm.
I can never take a professor's word for it when they say like it only took me like 25 minutes while I made
So
for a year. This is the first time I'm taking.
Right, yeah, so I always make it so that there's always a factor of 3, because I know for you guys, so I wrote the questions, and so I know exactly, so I always say like it's 25 minutes just to write everything down. But if you actually have to like think about it and do the calculations, then it's gonna take more time, obviously, so.
And we don't get a cheat sheet rendered.
You do,
We do. Okay.
yeah, one 8.5 by 11 sheet, both sides.
Okay, perfect. Thank you.
Yep.